this is the initial position, right? So let's define the initial position as P, right? And now this particle moves like this, right? And it is finally reaching to this final position P dash. Okay, so now let's call it like that, right? So now I will consider this as the origin, right? Right. So now this is the origin, right? So this is the x-axis, right? And this is the y-axis, and this is the origin, right? Okay. So now the displacement, right, or the distance, right, to this initial position, right, that is represented by this point P over here, right? So let's say that distance or that radial distance is r. Okay, so let's say that radial distance is r, right, and it is making an inclination theta with the x-axis, right? Okay, right. So now this is the final position, right? Now we will again try to connect this origin and this final position by kind of a length, right? Or let's call it a radius, right? So let's say something like a radius, right? So now I am going to connect this origin to the R, right? Okay. So now this particle, right, moves from here to here, right, such that this is the initial position, right? So let's call it the initial position, okay, and this is the final position, right? So now this particle moves from here to here within a time gap or within delta t period of time, right? And now here you can see there is an increment in this radial distance, right? Or let's call it that displacement, right? So let's say the present displacement from this origin, right, or the new radial length is, so let's call it r plus delta r, okay, right? Now then, but better use the term displacement rather than the distance, right? So let's say the initial displacement is r and the final displacement is r plus delta r. Now delta r is that particular change in the displacement after delta t period of time, right? So then if it is so, what is the initial radial velocity? What is the radial velocity? That means the velocity along the radial direction, if you consider it as a radius, so that will be radial velocity, right? Let's say radial velocity, so that is r dot, right? Then what is the final radial velocity? Final radial velocity, so that will be, so let's call it as r dot plus, right, delta r dot, right? So that is the final radial velocity, r dot plus delta r dot, right? Now what is the initial tangential velocity? Now what is the tangential velocity? Tangential velocity is the velocity, right, that is in a direction where the direction of the tangential velocity is perpendicular to that radius, right? This tangential velocity, if I call it as Vt, the tangential velocity that is perpendicular to this radius, right? So this tangential velocity Vt, that is given by the radius times, right, the angular velocity omega, right? So according to this initial situation, it will be r times theta dot, right? because this initial position P is making an inclination of theta with respect to the horizontal, right? So then what is the angular velocity? So this theta dot is the angular velocity. Theta dot is the initial angular velocity, right? Right. So then what is the final tangential velocity? So let's call it as the final tangential velocity will be r theta dot, right, which is the initial tangential velocity plus change in the tangential velocity. So let's call it delta r theta dot, right? So now you got the point. The difference in the angular displacement in between the initial position and the final position. So let's call it as delta theta, right? So then what is this small angle? That will be delta theta. Understand, right? So now here we are going to do some construction, right, for the betterment of our calculations, right? So let's make a line, right, that passes through this line that is based on the final position, right? So let's sketch a line that is passing through this line where it is parallel to the initial line, okay, or that is parallel to the initial radius, right? So now this line is parallel to the initial line. So then what is this angle? Delta theta, right? So first of all we need to identify this diagram, right? So now we'll see how to do that, right? So now let's see how to obtain the radial acceleration component, right? So let's write acceleration in the radial direction. Right. So that equals, right, the change in velocity along the radial direction, right, divided by, right, the time taken in order for that change to take place, for that change to take place, right? Okay, so now here you have to be very careful when you are taking the components, right? So now let's see how to take that. So now this one, right? Now what is this r? That is the original displacement, right? And this is the final position, right? And the final position is making an inclination of delta theta with respect to the original position, right? So now then what is the initial radial velocity component? That is r dot, right? So what is the initial radial velocity component? That is r dot, radial velocity, right? Then what is the final radial velocity along the final direction which is making an inclination of delta theta? So that will be final radial velocity, right? That means along this direction, along this new direction, right? That is, let's call it r theta plus some change, right? Some sort of a change, delta r theta, right? You got it? Okay. So if I sketch it like this, now see, now this is the original direction, right? R, and this is the final direction, which is making an inclination of delta theta. Okay. So that is R theta plus some change delta R theta. Okay. So now here, okay. So then, what is the final radial velocity? So one is this one, right? Now here, now we have a kind of a doubt, because now we have to consider certain components, right? Okay. So because now this is the fact, the original direction is something else. So this is the original direction, carefully take this, and this is the final direction, right? So these two directions are not parallel, right? So you have to be very careful when you are taking the difference, right? Because this change in the radial velocity, that does not take along the same parallel directions, right? So we will do like that. So we will do something like this. Now let's consider taking of all these differences along the same direction, right? We will consider the original direction, and we will take the respected radial velocity and other affected velocity components along this direction, right? Okay, so just sketch a line that is parallel to this line, right, that passes over here. So then what is this inclination? Delta theta, right? So then if you sketch a parallel line to this one that passes through the final direction, right? So then what is this inclination? That is delta theta, right? So then what is, again, if you sketch a parallel line like that, so then what is this angle? That is also delta theta. I hope you got it, right? So then what is this angle? This will be 90 minus delta theta, right? Because now we have to consider components, right? Okay. So what is the final radial velocity component along this direction? Now we have to take the components, right? You got it? Delta theta. This line is parallel to this one. So what is the first component? R dot plus delta R dot cos delta theta, right? Because we are going to take the horizontal component. This times the horizontal component, right? This times the horizontal component, right? Because we have to take the change along one considered direction. So what is that one considered direction? That is the original direction of the motion, right? So that will be R dot plus delta R dot times, right, cos delta theta. Is that all? No. There is an effect due to this tangential velocity component also, right? So what is the tangential velocity? Vt, that is R theta dot. Then Vt dash is the final tangential velocity. So what is that? So that will be R theta dot plus some change delta R theta dot. Okay. So now we can take the effect due to this component also. So that will be Vt dash cos 90 minus delta theta, but along the opposite direction, right? So minus Vt dash, because why? This is along this direction, and this Vt dash cos 90 minus delta theta is along the opposite direction. That means over here, directed to here, right? Okay. Now it is Vt dash cos 90 minus delta theta. minus, actually no, this is the final velocity, final radial velocity, right? This is the final radial velocity. What is the initial radial velocity? That is r dot, right? Right. And this change happens within a time period of delta t, right? So this divided by delta t, right? So you got it, right? So now I will erase this part, okay? Acceleration in the radial direction, right? So now there is one thing, right? Now here acceleration in the radial direction is the change in velocity, this thing divided by this one, right? And now we have taken the components, right? Right, we know that the final velocity minus the initial radial velocity divided by delta t. Now we have to take the limit of this. Limit delta t tends to 0. Right. Got it? Change in velocity, this equation. Then we have taken the components. Then you have to take limit of this one. Right. You have to take the limit of this one. This whole statement while sending this delta t value, because we have to consider delta t tends to 0, right? Got it? Right. So now let's solve this, right? So I will erase this equation, right? Right. Limit delta t tends to 0, right? R dot plus delta r dot times cos delta theta minus, right? What is Vt dash? Vt dash is r theta dot plus delta r theta dot, that particular change, right? Times cos 90 minus delta theta is sin delta theta minus r dot divided by delta t. Right. Now we know that when delta theta is very small, we know that cos delta theta is 1 and sin delta theta equals delta theta, right? Limit delta t tends to 0, right? Cos delta theta, because now delta theta is a very small angle, right? So cos delta theta is 1. R dot plus delta r dot minus r theta dot plus delta r theta dot. Sin delta theta becomes delta theta minus r dot divided by delta t, right? Now I will again erase this part, right? Because I have to adjust some space, right? So now first let's simplify. R dot plus delta r dot minus r theta dot minus delta times r theta dot. Here minus r theta dot times delta theta. Now we have to expand this. This is correct. Minus r theta dot delta theta, okay? Minus r theta dot delta theta minus delta theta times delta r theta dot, right? Minus r dot divided by delta t. Okay. Now this r dot you can cancel, right? Okay. Now when compared to other components, right, this is a very small value. This is what? Very small. So we can neglect, right? So we can neglect that, right? So then we have limit. Every time we have to put this limit delta t tends to 0. Every time we have to put that. Don't forget delta t tends to 0, right? We have delta r dot minus r theta dot delta theta. Okay, divided by delta t, right? So now this limit we can apply separately. Understand? This limit we can apply now separately. Okay, limit delta t tends to 0, delta r dot divided by delta t minus limit delta t tends to 0, r theta dot delta theta by delta t, right? Okay. So now delta r theta dot divided by delta t, we can write it as dr theta dot by dt. Right. Delta r theta dot divided by delta t we can write as derivative dr dot divided by dt minus this one we can write as r theta dot times d theta by dt. Okay. So what is r dot? Now we know that r dot is actually dr by dt, right? So r dot is the differentiation of the displacement with respect to time once, right? So dr dot by dt means r double dot, right? Okay, minus r theta dot times d theta by dt is theta dot. So what is the final answer? R double dot minus r times theta dot whole thing squared, right? So that is the final answer, right, for the acceleration in the radial direction, right? Or the equation for the radial acceleration, right? I hope you got it.